After reviewing and thinking about this part of the code, we found a small issue related to this line. When the code is executed as it is, the text inside the counter appears attached to the borders. Therefore, we try to add extra interspacing before this line. But when the code runs again, nothing seems to change. We need to rearrange the code so that the inner padding is added after the background and border in order to achieve the desired result. This shows that the order of the modifiers is very important and can lead to differences in the output.
Before adding anything else to the game, let's do some organizational work. Create a new Kotlin file named GameScreen. Then move the GameScreen function into that file. Next, let's move a scale value for the jet into a constant. Val jet scale equals 0.50f. And instead of showing the jet at a random location, let's position it at the bottom center of the screen. To do that, we need to retrieve the screen dimensions. For that we need to define some constants. Val config equals local configuration.current. And val density equals local density.current. The config constant provides information about the device configuration, such as screen width and height in pixels, orientation, portrait or landscape, language or locale. While local density.current is used to access the current screen's density information, or you can say how many pixels exist in each density-independent pixel. With this, we can convert values between dp and px, which is essential for positioning UI elements precisely according to screen dimensions. Now we can fetch the screen width of mobile using following code. Val screen width px equals with density config.screenWidth dp.dp. to px. And to get screen height we use the same syntax but for get screen height dp. After obtaining the screen dimensions, let us define a variable to store the jet's position using coordinates. Var jet position. And also using by remember and mutable state of. To convert the screen dimensions into coordinates we using the offset function. Passing the width first, then the height. We divide the width by 2, so that the jet appears horizontally centered. We subtract 200 pixels from the height so that the jet appears near the bottom of the screen, leaving a small margin from the edge. Thus, we have a variable that stores the airplane's position. Following the same principle discussed in the previous episode. Whenever the variable's value changes, the jet's position on the screen updates automatically.
Let's put the constant jet scale and variable jet position in their places. Let's see the result of this changes. Oops. It's like their error in jet position variable. Let's fix it. We have duplicate the constant screen height px. If we run the code again, we will see the jet at a suitable starting point. The big question now: how can we enable the user to control the jet? This brings us to one of the most enjoyable part of the game. In different games, there are several methods of control, such as finger dragging, using the tilt sensor. However, in our game, we want the jet to be controlled through a joystick that appears on the screen. How do we program this? Very simple.
Step 1. Create a regular container. Then, adjust its properties as we did earlier with the counter. Place it at the bottom left corner of the screen. Set the padding to 16 dp. Make it size 150 dp and change the background color to gray. And make it shape circular. Nothing unusual, so let's continue.
Now, let's add the joystick knob that we will use to control the jet. In fact, it is the same container as before, but with a smaller size. The important thing to add here is graphics layer. But first, what is it? Graphics layer allows us to directly apply transformations such as scaling, rotation, opacity, and translation to a composable element at the graphics layer level, providing more flexible visual effects. Inside this layer, we will assign values for translation X and translation Y, which represent the joystick's coordinates. These values will be taken from a variable that we will define as joystick offset. As we learned earlier, whenever we want something to change dynamically on the screen, we must make it of type remember and mutable state of. So, let's copy the code we used to define the variable that sets the jet's position. Rename the variable, and make the coordinates as 0f 0f, so that the joystick starts at the center of its container. Now, we define the values of translation X and translation Y. Next, let's set the joystick knob size to 60.dp, its color to white, and its shape to circular as well. Let's take a look at the implementation. As we can see, the joystick knob appears, but at this stage, it cannot move yet, nor can it control the airplane.
Wouldn't we be able to move the joystick by adding a function to track its drag, change its position, and then change the position of the jet?
At first, we thought about that, but we discovered that the best way is to handle the touch events inside the gray container. This is because the container defines the area where the user is allowed to touch and move the joystick. Inside this gray box, we add pointer input, a function that lets us receive touch events and finger drags on the screen. Within it, we use detect drag gestures, which detects drag gestures and gives us information about the direction and distance of the drag. This block, on drag end, runs when the player lifts their finger off the screen. Here, we reset the joystick handle back to the center, its original position. This is how real joysticks work, they always return to the middle when released.
When the finger is dragged, the system gives us a value called drag amount. This represents how far the finger moved. We calculate the new position of the joystick knob like this. First, make val named new offset equals joystick offset plus drag amount. Joystick offset is the current joystick position, and drag amount is how much the user dragged. Now, we don't want the joystick to move infinitely far away. It must stay inside a circular boundary. To define this limit, we set a radius to 75 px. This means the joystick can move at most 75 pixels away from the center. We then calculate how far the joystick has been dragged from the center by get distance function. Here we change the position of the joystick knob. If the joystick's new position is outside the circle, distance greater than radius, we push it back to the circle's edge. And else the joystick's new position is inside the circle, so we just save the new position as it is. Now, the joystick knob can move freely within the gray boundaries, and no matter how hard you drag, it will never go outside. The next step is moving the jet, and this is actually very simple. We use the value of joystick offset to move the jet, but instead of adding the full value to the variable jet position, we only add 20% of it. This way, both the joystick knob position and the airplane's position change smoothly together. And now, after long waiting, yes, it works like magic.
At this moment, I want to point out that you now have an idea of how games actually work. This joystick can be useful whether you want to move a plane, a soccer player, a racing car, or anything else. You now have the principle and the method to implement it. All you need is imagination to make the most of it. I can say, just like in the world of Frieren, programming truly relies on imagination.
But wait, we are not done yet. We still have meteors to add, and some other settings to adjust. But after this video, I'll say it like Master Sherfu said, there is now a level 0. Yes, we've just begun, but we're determined to reach the highest levels together.
So if you have any questions or suggestions, we'd be happy to hear them. Also, check out our store in Patreon. We've added some new free space-themed wallpapers. Take a look. This was No Name, with my partner Coda, and behind the scenes Matthew.
If today's episode helped you even a little,
Then hit like. Leave a comment. Let us know you're learning. Next time, we will level up.